Today I want to think a little bit about area, other than just area under the curve. We know how to find the area under the curve when we are given the height as a function of the width. We think about area, or the length as a function of the width, a continuously variable function of the width. But we want to think about the process of finding area more generally. We want to get out of this always have to be a function. So here we have a box. X goes from 0 to 3 and Y goes from 0 to 9. And I've divided the box. Well, I have one just plain old box and then two boxes where I've divided with a different curve. This middle box, I've just divided the curve with a line going from 0, 9 to 3, 0. And in the third box, I've divided the box, or in the third box, I've divided into two parts with a parabola from 0, 9 to 3, 0. I want to find the 5 areas, A1, A2, A3, A4, and A5, using as much or as little calculus as you want. The as little calculus part is the fact that we can get away with finding just one of these, or using a definite integral just one time. The rest of them we don't really need a definite integral for. So go ahead and pause the video if you want to give this a try. Mind your decision style. All right, welcome back. Let's talk about finding each of these areas. Now, for most of these, we do not need to use anything fancy. We have shortcuts for most of these. A1, what's the area A1? How much is that? It's just a rectangle. This is the only formula for area we need. So area is area 1 is just 3 times 9. It's a rectangle. 3 times 9 is 27. Here it's just a rectangle. For A2, the most likely thing we did was notice that we have a triangle. A3 is going to be the same triangle. So A2 and A3 are both going to be the same triangle, different triangles, the same dimensions. So we'll just take 1/2 the base times the height, or 13.5. We're just doing a triangle. Now in A4, one of the parts that we have, for A4, we can just find the area under that parabola. So we'd have to know what the parabola is so we know how to communicate that. It starts off at 0, 9. And by the time x gets, we get down to y equals 0, we've gone to 3. So this is clearly the parabola, y equals 9 minus x squared. I didn't even change the coefficient of x. So for A4, we'll use a definite integral, because this is a standard problem for a definite integral. Find the area under a curve and above the x-axis, and interval on the x-axis. So we just integrate the function 9 minus x squared dx. And we said use as little calculus as we want. So I'm not even going to find the antiderivative. I am just going to calculate this on my calculating machine. So that is the one that we're going to have to use a definite integral on, or at least the easiest one that we can use a definite integral on. Now that I know that the area A4 is 18, I don't have to calculate anything fancy for the area A5. I just have to subtract. I know this is 18 out of the box. So A5, I'm just going to take the area of the rectangle and subtract the area under the curve. So 27 minus 18, that gives us 9. So here's the one. That would be the best one for a definite integral. And then A5 we can just get by subtraction since we've already got A4. This is ultimately the idea. Use as little of the fancy stuff as you need, and then try to find workarounds for the rest. So if I start modifying this problem, so if I take this and modify it slightly, this doesn't change anything for the rectangle. I could put a diagonal in each one of these and I would have the same two triangles. The 27 rectangle, if I cut it in half across a diagonal with a line from corner to corner, I'm going to get 13 and a half in each triangle. And if I cut it with the same parabola from one corner to the next, so this is a sideways parabola, but it's still just a parabola. And it's only half a parabola, but we only had a half a parabola before. So still just a parabola. But it's a differently shaped parabola. It's a x equals y squared parabola instead of a y equals x squared parabola, also known as y equals the square root of x. So if I want A6 is the area under the curve. So I just integrate from 0 to 9 this time, the square root of x dx. And since I want to minimize the amount of calculus that I'm doing, I will just grab my calculator and ask it to calculate the f integral. So I get the square root of x with respect to x from 0 to 9. And it is unsurprisingly still just 18. Don't worry about the 0.00000000000025. The calculator is clearly trying to tell you 18. It's just using approximation method, so it can't tell the difference. And its algorithm tells it to stop now, even though it's not done. So we found this with the definite integral. We knew that this was going to be the same as A4 because we have just turned. We just took A4 and turned it sideways. Just rotated it 90 degrees, moved where our axes were. But I'm still just cutting this box, this 27 unit box, splitting it with a parabola. So at this point, we should have we knew that this was going to be the same as A4. We should recognize this is going to be the same as A4 because I'm just taking a 9 to a 3 and cutting it with a parabola instead of a line. Once again, once we have this area under here as 18, then we can just subtract to get A7. Questions? How's everybody? Okay. So when we cut it with a parabola, we get a 2/3, 1/3 split. When we cut it with a line, we get a 1/2, 1/2 split. Incidentally, since I picked such good values for this 2/3, 1/3 split, notice that if we integrate an x to the 1/2 power, that's going to be 2/3 x to the 3/2. Notice that that x to the 3/2 is going to have a 9, the 3/2. And there are three threes running around. 1 3 for the height, and then 2 3s down on the bottom. So this is just using our understanding of geometry. We're exploiting what we know about how area works in geometry. We take the whole and subtract off one of the pieces. That gives us what's left over. What I want to think about is how we can go about integrating things, always using integration. Now, this seems excessive, but it's an important skill to have, because we want to have the skill not just of finding area. That is a limited skill, but we want to improve our skill in analytic geometry and combine that with calculus. That's like literally the title of this class, calculus with analytic geometry. It has an unfortunate abbreviation, but that's beside the point. I think I need to grow up because I just need to grow up. So we want to do more analytic geometry and use more calculus. Finding the areas isn't the point of the problem. In a geometry class, that's exactly what I would do. We would just practice this skill of finding these areas, knowing that we can subtract. And this is just, if we were doing an arithmetic class, I would tell you that two things add up to the whole. The two parts add up to the whole. So if I give you one of the parts, what are you going to do? You're going to subtract. If I give you the two parts, you're going to add them to get the total. If I give you the total in one of the parts, you're going to subtract to find the missing parts. That's just understanding arithmetic. That was way back when we said 2 + 3 is equal to 5. And you're like, oh, got it. And then I'm like, oh, 5 - 3 is equal to what? And you're like, oh, probably 2, I guess. I'm like, oh, that's correct. And then we were in geometry. I'm like, oh, the area of this thing is, the area A7 is 3. The area, or let's use the numbers. Area A7 is 9. Area A6 is 18. What's the total area? And you're like, I'll add them. I'm like, oh, yeah, 27. Then I'm like, oh, okay, it's 27 total. And A6 is 18. What's A7? I'm like, well, subtract it. Same lesson as 2 + 3 is equal to 5. Means 5 - 3 is equal to 2. So now we're going to use this and try to go further. We're going to use more analytic geometry. I was going to do the other one, but I made that the short one. I'm going to use the same setup. I'm going to take this 27 and I'm going to cut it with a parabola. To keep the principle the same, to increase our analytic geometry, I'm going to orient the parabola a slightly different way. I'm going to put the vertex of the parabola at 9, 0. I'm just going to flip this around. Here's our vertex. This is a sideways parabola. I got my vertex at 9, 0. And it looks like it's an opening sideways parabola. So instead of thinking of x equals y squared, we're going to think of x. Instead of y equals x squared, we're thinking x equals y squared. In functions, because it's Calc 1, and we frame a lot of things as functions of x, instead of thinking of x equals y squared, we're going to frame this in terms of y equals square root of x. We're looking at this, we've only got the top half of the parabola, so it's okay to switch to this square root of x type of language. But it's facing the wrong way. It's opening that way. And our vertex is at 9. So I've got to shift some stuff around. So as a function, so I'm going to flip it horizontally. That's going to change the sign of our input. And I'm going to shift it 9 units. Then if I'm unsure, all right, we're not looking back far enough. I go, all right, seems to get it. That seems to get it. 0, 3, 9, 0. All right, that's it. Nice to double check. So we know that A8 is going to be 27, or sorry, out of the 27, the A8 is going to be 18, and the A9 is 9. Oh, that worked out. Based on our previous calculations, A8 should be 18 and A9 should be 9. But what we want to do is think about setting up a definite integral for A9. So that will give us the 9 that we're looking for. Let's set up a definite integral for A9. And let's start learning to be flexible. I'm going to describe A9 with 2 different definite integrals. One of them is going to be an integral in terms of x, and the other one is going to be an integral dy. This is going to require us to do some analytic geometry, and it's going to require us to understand how we set up definite integrals, what we're calculating in a definite integral. This is how we set up the thinking before. Area under the curve, f of x, and above the x-axis is the integral. from A to B of f of x to x. What this is based on is length times width. And we have this variable length. And we're looking at a little piece of the width. And then we integrate over all the different values of the width. Now, these are just names for things. I used to get bent out of shape when we would set up problems and the width was longer than the length. I'm like, oh, dude, why is it the width if it's longer than the length? Shouldn't that be the length and the other one be the width? Then people started getting my name wrong all the time. I go, oh, I get it now. It's just a name. So there's no reason that we can't set this up in the other direction. We can set this up in the other direction. Instead of integrating the length over the width, we can integrate the width over the length. And then we'll integrate from the length start to the end length. Because area is length times width, and that means area is also width times length, and it doesn't matter what we call them. Now, if I start using things like dx and dy, now it does matter what we're calling them. Because once I start referring to the length and the width in terms of x and in terms of y, x and y have meaning in this context. X is the horizontal stuff, y is the vertical stuff. Now it matters. So we also want to be able to think about this area, not just as a function of x dx, but what if we also set up an integral, let's say from c to d of some function of y dy. All right, so let's find this. Let's set this up as a dx problem. So what that means, if we set this up as a dx integral, that means for a particular value of x, we're going to find the height that we want and use that for some small change in x. So for a particular value of x, I'm going to use a fixed height for some small change in x. I'm going to say the length is going to be constant for this whole delta x. I just need a length to represent the rectangle. So I'm just going to go up to the function here. And this is the length that I want. That's going to be my length. I used red for length, so that was close. I'm going to say this is the length. I'm going to use that for some small change in the length or in the width. This is going to seem like an excessive amount of effort to get an area of 9 that we already know, but that's not the point. The area of 9, that's just going to make sure that this works out. But what I want for area A9 That's the little piece. I'm going to imagine A9 is a bunch of rectangles, but the rectangles are up there. Now, if we look at the coordinates that we have, what I need to know is the width is going to be, or the change in the length is going to be this delta x. I need to know this distance up here. So I have this distance times the delta x. If I have been. So I need to know, what I need to know is this up here. That's what we need to know. It's not going to be just whatever the function is, because I don't want what's from the x-axis up to the function. I want from the function up to 3. Now, if we look at some coordinates that are going on here, this is where I would label x. Because we're on set of coordinates, and this is where we would label y. So what I need to do is write the width in terms of the x variable. I need to write the width in terms of x. Notice that I can't just use the function. Y is equal to 9, square root of 9 minus x. Square root of 9 minus x is the amount under the function. I want the amount above the function and under the line y equals 3. I'm going to write it. I'm going to change the order that I say it. Change it to the order that I'm going to write it. We don't want what's under the function. We don't want what's under the function. We want what's under the 3 and above the function. Y equals square root of 9 minus x is what's under the function. We're not looking for that. We want the width that's under the 3 and above the function, because we are trying to find A9. So we're going to say that the width is going to be 3 minus the function. I'm going to do it in the Y color, I guess, is going to be orange today. So the width is 3 minus that Y. But that's no good. We're setting up a delta X. Not in terms of Y, I need it in terms of X. So the width is going to be 3 minus the square root of 9 minus X. We need to write the width in terms of x, not y. We need to write the width in terms of x, not y, because this is a dx integral we're trying to set up. So the width is this 3 minus the square root of 9 minus x times the delta x, which becomes a dx in the integral. And we do this for all the values of x that are in play. The values of x that are in play start off at 0 and go up to 9. So down here is where x is equal to 0. And here is where x equals 9. Nine. 8 point, a bunch of nines and a 7, 4, 9. 9, like we expected. The reason that we do this on for an area where we already know what the area is to make sure that our method went right. If I did this method and I got like 15 or something like that, then something is not right with the method. Something is wrong in the way we're thinking about the problem. Questions? The next thing we're going to want to do is still working with A9. I think I can get away without writing this again. I want to turn the rectangle sideways. And instead of looking at the width at different places on the length, what if I looked at the length for different places on the width? What if I said here is I want this rectangle. So we're changing what the delta variable is. So here we're thinking in terms of delta y. And now what we need to go with our delta y is the length, which is up here. So now we're going to be thinking of integrating the length dy instead of integrating the width, or integrating the length delta width instead of thinking integrating the width delta length. Any questions? It's not about finding that the area was 9. That's why we opened up with, if we split this 27 unit rectangle, a 3 by 9 rectangle, with a parabola from corner to corner, we're going to get a 9 and an 18, 2/3 and a 1/3. Now I want to find A9 by setting up the definite integral. That's what we want to be able to do. Set up the definite integral, not just find the area. That makes sense? Finding the area is not the problem. The answer that you type on Canvas and hit submit, that's not the point of the problem. The point of the problem is setting up the definite integral. I was gonna write the answer down here and then not reveal it because we're at the end of class, but I've only got a few minutes. I have 0 minutes left, so. I was literally gonna not show you what I was writing. That's a very on the dick move. I'm like, oh dang, look at the time, so. All right, that's gonna do it for today. I will see you all on tomorrow. Think about area, not finding the area, but setting up the definite integral. That's it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.